Good morning, students. I welcome you all for another lecture on the course Computer Architecture and Organization. In this class, I am going to discuss about hardwired control unit. We know that in our system, the important block is central processing unit, because the central processing unit can do different functions like data processing as well as control function. In that, we have different blocks like a register set, ALU and a CU. Again, in the CPU, the important block was control unit CU, because that is the unit which generates the required control signals which are necessary for proper operation of our system. Those control signals are generated by our control unit. Basically, there are two types of designs for a control unit. One type of design is hardwired control, and the second variety of a design was microprogrammed control. In today's class, I would like to discuss about the hardwired control unit. Right, straight away we enter into the concept. First, we will see the overview of this. To execute instructions, the processor must have some means of generating the control signals needed in the proper sequence. For example, here I would like to execute an instruction. That is add register R1, R2, R3. The meaning of this instruction is perform addition between R1 and R2, and result was transferred to another register R3. If I want to do this execution of this instruction, my control unit must generate a control signal to transfer the content of register R1 to one of the input of ALU, and again my control unit generate a control signal to transfer the content of register R2 to another input of ALU. Once these two inputs are available at the input side of ALU, again my control unit generate control signal add. That gives the indication to control unit, that gives the indication to ALU, you have to do addition on your inputs. Again, after completion of addition, the result was available at an output, that is again transferred to another CPU register R3. For that, again the control unit generate a control signal to register R3, what are the value that was available on internal bus, you can go and accept it. So in order to execution of this instruction, I need a different control signals in different time incident. These control signals are generated by my control unit in a sequence. So for that, there are two designs for the control unit. There are two categories of control units. One is hardwired control and second one is microprogrammed control. As per this class, I would like to discuss about this hardwired control. Right. The hardwired control system can operate at a higher speed but with little flexibility. The meaning of this particular one is your hardwired control unit generate the control signals at a faster rate. We will go and discuss why it will generate a control signal at a faster rate within few minutes. At the same time, at the end of this class, we can identify that the flexibility for this hardwired control unit is less. So, at the end of this lecture, you may identify that why hardwired system can operate at a higher speed as well as with a little flexibility. You can easily identify. Right. Each step in the execution of an instruction sequence is completed in one clock period. That means what are the steps we are going to take in execution of an instruction? Each step in the instruction execution must be finishes in a single clock cycle. Just now I took an example, that is addition of the content of register R1 with R2 and send a result to R3. In that case, my control unit must generate a control signal for both register R1 and R2. This was happened in a time incident at T1. In the second time incident, again my control unit sent a control signal to ALU to do addition. In a third time incident, Again, my control unit generate a control signal that is given to register R3 to go on to the data what is available on an internal bus. That means here there are 3 steps. These are 3 steps are performed in 3 different time instants. That means the operations which are performed in a single step, those must be finishes in a single clock cycle. That's the meaning of this. And next, a counter may be used to keep track of the control steps as shown below. So what my control steps? Each state or count of this counter corresponds to one control step. The required control signals are determined by the following information. So in order to execute these 3 different operations, that is generator of control signals for register R1 and R2, later generation of control signal for A to do addition, and later generation of control signal for register R3 to go on to get data what is available on an internal bus. These are the different operations. These different operations are performed in different clock cycles. In order to keep track of these things, I would like to use some counter in internal to my system. That will be taking care of this. So that we are going to discuss. So what are the different control steps? The first one, the content of control step, counter, the contents of instruction register, the contents of condition code flags, external input signals such as MFC and interrupt requests. What these 4 are? In order to generate a control signal by control unit, it has to consider different informations before generation of a control signal. That means the generation of control signal depends on few things. In that, what those few things are? Number 1 is the contents of a control step counter. What is the content of it? And number 2 is the contents of instruction register IR. Number 3 is the contents of condition code flags. And number 4 is external input signals such as MFC and interrupt requests. MFC means memory function complete. That means, for example, you can assume, friends, this is my hardwired control unit. This control unit generates control signals. It will generate a control signals this. This control signal generation is dependent on 4 important things. What those 4 things are? Number 1 is control step counter. What's the content of it? So let you can assume this is my control step counter. What is the content of this? This is given as one of the input to this. And second one is the content of that is instruction register IR. We know the functionality of this instruction register IR. Always it will hold the instruction which was executed by CPU right now. And also it depends on a conditional codes. This is the condition code register. What are the values that are available on this? That is also given to the input of this. And the last thing is, it is also receives a control signal from external world like MFC as well as interrupt request signal. By considering of all these inputs, the control unit generate control signals at its output. So that is the meaning of that. A decoder encoder block is a combination circuit that generates the required control outputs depending on the state of all its input. That means here I have a decoder / encoder circuit. This is a decoder / encoder circuit. It is a block which will generate the control signals based on all these information in case of hardwired control. So this is the block diagram, friends. So this is the clock. For a control step counter, the input was a clock. The output of this one is our timing states T1, T2 and so on, Tn. These are the different counter steps which are present in this control step counter. For it, the input is nothing but a clock. Because here the generation of these control signals are done with reference to clock. That means what time instant the control signal C1 generates, or what time instant the control signal C2 generates, or what time instant the control signal C3 generates. This control signal generation is purely depends on one of the parameter is here, that is the timing signals. These are timing signals I was getting from a clock signal through this control step counter. This is one of my input for this decoder / encoder circuit. What will be the another input? Instruction register. Definitely based on the instruction itself only, I must generate a required control signals in order to execution of that instruction in a proper way. So my decoder and encoder circuit collect that information from instruction register IR. At the same time, this control signal generation is also depends on two more factors. One factor is nothing but external inputs. That means sometimes I can receive MFC signals as well as interrupt request signals from external world. I must consider those signals also for generation of control signals. And sometimes it also depends on the conditional codes. That means the status flags. By receiving of that information also, I can go on to generate the control signals at the output of this decoder/encoder circuit. That means here this decoder/encoder circuit generates the control signal at their output by considering four different informations. One is nothing but the clock signal which was coming through this control step counter, and second one is IR information, and third one is from external inputs, and fourth one is nothing but conditional codes. By considering of all these things, my decoder/encoder circuit will generate the control signals. So here important thing is, here this decoder/encoder is a combinational logic circuit. It is a combinational logic circuit because your decoder is a combinational logic circuit and your encoder is a combinational logic circuit. It decodes as well as encodes the signals what it receives at its input side. Based on that, it will produce the control signals at its output. So purely it is a combinational logic circuit. So this is a detailed description of my hardwired control unit. So here only the thing is, I explained previously, here I have an IR straight away, but here I can go and use an instruction decoder. And here it is my encoder, and as usually I receive signals from condition codes, and as usually I receive signals from an external, that is MFC signal as well as interrupt related signals, and as well as I can receive my timing signals through this control step counter, through this step decoder. Here there are two decoder circuits I use. In previous case, this is not exist and this is also not exist. Straight away IR information is given to decoder/encoder circuit, and as well as the control step counter information also is straight away applied to encoder/decoder circuit, and these inputs are as it is. So in order to go more in detailed way, so instead of straight away applying IR value, I can go and use an instruction decoder, because whatever the instruction I was executing in my CPU, first of all, I fetch that instruction from the memory. After fetching that instruction that was stored in instruction register, actually that instruction was in coded form. So with the help of this instruction decoder, I decode that instruction. Here I have INS1, INS2 and so on, INSM. That means I have a different sub operations I performed in that instruction execution. Those I was given as input to this. Let you can assume in a previous case, my example was add R1, R2, R3. If I decode that instruction and the output of that instruction decoder, I identify that my operation is addition. In order to do that addition, I must take a data from register R1 and R2. Those are two things I have to give to the input of ALU. Once I apply both the register R1 and R2 values as an input to ALU, later I must generate a control signal for ALU to do addition. And thereafter again my CU has to generate a control signal to go and get whatever the data that was available on an internal bus. So that's why here these are INS1, INS2 and INSM. These are in an instruction execution different partitions. Those are considered as an input for this encoder for generation of different control signals. And one more thing you have to remember, friends, these are control signals not only move to the external world of my CPU, it is also given to the internal parts of a CPU also. Sometimes I can go and take data from external memories, or sometimes I can go and take data from our input devices. So such a time this encoder circuit generate control signals, those are given to the external world. But in the previous case, my operands are only the internal parts of a CPU, both are my internal registers. That means the control signals what it was produces at output end of this encoder, those control signals are goes to both the internal devices of a CPU as well as those are given to external world. So in this process, the generation of these control signals are done with reference to the clock signal. That's why here I have a different timing instance, T1, T2 and so on Tn. Just now I told you that at each step of my instruction execution, what are the tasks task I was doing in that each step, that must be finishes in a complete clock cycle. That indicates a T1 cycle, a T2 cycle, and so on, Tn cycle. So only I was elaborated my hardwired control unit by incorporating of our two decoders. One is instruction decoder and second one is a step decoder. The output of my instruction decoder is I have a subclassification of my instruction steps, that is INS1, INS2 and so on, INSM. And the output of my step decoder I have a timing signals T1, T2 and so on, Tn. So that is an important thing. So the step decoder provides a separated control line for each step or a time slant in control sequence. No doubt, because I have a T1. In that case, my control unit generates a set of control signals. Those control signals are helpful for me to do a different task in that time incident or in that time slot. In a T2 time incident, again my control unit generates a different control signals which are used to perform a different operations in time slot 2. So, here the step decoder provides a separate signal line for each step or a time slot in a control sequence. Similarly, the output of instruction decoder consists of a separate line for each machine instruction. Your machine instruction here is INS1, INS2 and so on, INSM. For each and every machine instruction, I have a separate dedicated line which I was given to the input of my encoder circuit, which produces a required control signals for me. Next, for any instruction loaded in the instruction register IR, one of the output lines INS through INSM is set to 1 and all other lines are set to 0. Absolutely, it is true. Because in every instruction execution I have different stages. That means in every instruction execution I must go and execute a set of machine instructions. Those machine instructions here I was representing with INS1, INS2 and so on, INSM. At any time incident, only one of my machine instruction was active. That means only one machine instruction signal, INS signal is set to 1 and the rest of the things I set to 0. That's the meaning of this. The output signals to the encoder block are combined to generate the individual control signals while PC out, add, end and so on. So what are the control signals I was getting at the output of my encoder? Those control signals are helpful for me to make all these things. Those control signals are individually useful for me. Yn, that is the signal is necessary to load Yn register with its input value. And PC out, what are the value that was exist on the program counter PC. In order to read it, I need a control signal PC out. Again, if I want to do an addition operation by using ALU, if based on its input value, for that case I need a add signal. For ending of an operation to indicate that I need a end signal. Like this, different control signals are generated by my encoder circuit. So that's the meaning of this. So you see here friends, this is a simple logic how I was getting my Zapping signal. Here I was getting a Zapping signal. This Zapping signal is depends on T1. That is this. It is depends on T6 along with add signal. And it is depends on T4 along with branch signal. That means this Zapping was active. The meaning of this is the Zapping signal was active in time incident T1 as well as time incident T6 along with the add and time incident T4 along with the branch. Like this, my Zapping was active in different cases. That means the Zapping signal was active in different time incidents. That's why here it is and so on. Zapping is one of my control signal that was generated by encoder output. By considering different inputs, in that case it will consider INS inputs as well as it will consider timing signal inputs as well as it will consider the flags values as well as it will consider external signals like NFC as well as interrupt signals. So what this diagram indicates is, this Zapping is nothing but a control signal which is generated by my encoder circuit. At what time instant it will generate, that is indicated here. It is activated in T1 time instant. It is also activated in T4. That instant it is along with the branch. It is also activated in Z4 along with AND case. Because all these signals I was given to the input of OR gate. That means we know that the Zapping is equal to 1. When it was happened, it's at least one of its input is set to 1. That means in these different time incidents, my Zapping signal is active. In previous slide we can see that YN signal, that is one of the input signal for a register Y to copy whatever the value was exist at its input side. Similarly, the Z register, which was present at the output side of an encoder. If you refer to past classes, it is very clear to us the registers that was present at the output side of our ALU circuit. In order to copy the output of ALU into Zin, definitely Zin signal is set to 1. So here this Zin is active at different time instants. And similarly, we can go and see another one, that is N. This N is active in a different time instance. It is active in T7, it is active in T5, it is active in T4, it is active in T5, like this. In this different time instant, and signal is also active. Once I was generating active signal, sometimes this signal is mixing with or combining with different signals like N bar branch is less than 0. That means it is a conditional or that was unconditional. So that means here the send signal also activated in different time incidents, like a previous case Zin. This Zin as well as N signals, these are the control signals which are produced by my encoder circuit. So here it is very clear, friends, that is your hardwired control unit is a combination logic circuit, that is one thing. And it consists of number of such type of circuits for generation of control signals. Once here, if you are observing this whole thing, it is very clear, friends, the control signals are generated by encoder circuit by considering different inputs. For generation of each and every control signal, there is a dedicated circuit, so that if I use a dedicated circuits for generation of control signals, the control signals generation was done at faster rate. At the beginning of this concept, we clearly mentioned that, I told you that at the end of this concept, we can easily get why hardwired control unit is a high speed control unit, as well as it is a less flexible. So one thing is very clear, friends, that is the speed of operation of hardwired control unit is fast. Because the reason for this is, what are the circuits I have in this encoder circuit which are helpful for me for generation of control signals? Those are purely hardware devices. Once these are the hardware devices, no doubt the control signals are generated at faster rate. And here the flexibility is low, or flexibility is less, or a little flexibility. The reason for this is the control signal generation is purely depends on what are the hardware circuits those are exist in my encoder circuit. If I want to add a new instruction, according to that instruction, I must know what are my machine instructions. If I know the machine instructions and the control signals is generated based on those machine instructions as well as different inputs, based on that, I must go and make internal hardware circuits. It is not possible for me once I was designed a control unit. If once I design a control unit, I have not altered it. I didn't add any additional circuit internal to it for generation of new control signals, so that the flexibility is less. If the control signals I was not generated, that means it is not possible for me to add a new instructions to my instruction set. Because in every instruction execution, we know that we need a different control signals. In order to proper execution of that instruction, to do an operation in a proper way, I need a different control signals. Those are generated by my control unit. So that here it is not that much easy to add a new instructions to the instruction set. That's why the flexibility is little. But once you are using hardware circuits for generation of control signals, no doubt these hardware control unit generate a control signals at faster rate. I hope you understand the meaning of that. Why hardwired control unit is as high speed as well as little flexibility. Right. Hardwired control can be viewed as a state machine. Yes. Because it is a state machine, because I have a different states. Each state depends on different control inputs, different inputs. That changes from one state to another in every clock cycle, depending on the contents of instruction register, the condition codes and external inputs. Because already timing signals is given by my step decoder. These are very, very important. You change the state from one state to another state. I have to consider three important information. One is IR value, second one is external inputs, and third one is nothing but condition codes. So that's the meaning of this. The outputs of a state machine is determined by wiring of logic elements. So that is true, because the outputs of a state machine, that is nothing but the output of your encoder, which is our control signals. Those control signals I was getting just by wiring of a different logic. That means AND gate outputs are given to the OR gates, then OR gate output is created as my control signal. Right? So here the outputs of a state machine is determined by wiring of the logic elements. Hence the name hardwired, because purely hardware devices are present in my hardwired control unit and their interconnections. That's why it is called hardwired. So that is this. The advantage of this control design was it can operate at a higher speed, because all are the hardware devices. Those hardware devices generates a control signals at a faster rate, so that this control unit is a high speed control unit. The disadvantage is that it has a little flexibility, and the complexity of the instruction set it can implement is limited. That means if I add more and more number of instructions, it is not possible for me, so that the flexibility for the control unit is limited. The disadvantage, I need not be, or I was unable to add a new instructions to do a more number of operations by using a CPU which may have the control unit was a hardwired control unit. Right? That's the meaning of this. So I hope you understand what this hardwired control unit is. One thing you have to remember, friends, the hardwired control unit is a control unit designing mechanism. In this, the control signals are generated by hardware devices, so that the control signals are generated at faster rate. That is one thing, it is an advantage. At the same time, the flexibility of a control unit designing was less, because once you design a control unit based on certain instruction set, you are unable to add a new instructions to it, because if you are adding new instruction to it, if you have to go and add new control logics in your hardwired control unit, it is not that much possible or that much easy. That's why the flexibility of this particular control unit is very less. Please keep all these things in your mind. I hope you understand this concept. Thank you for patient listening. In the next class, I would like to discuss one more concept, that is microprogrammed control unit. Thank you. Thank you for patient listening once again.